All right, here we go. You're back to videos with no picture of me because new computers won't allow me to process double video at once. So you don't care about that. All right, here we go. So today we are going to get a crash course in vectors. So first of all, quick review. Before we even get to vectors, we got to do a quick review of some SOHCAHTOA stuff. All right, so hopefully you know this from your math class. If not, I gotcha. So when you have a right triangle, it buys us a few equations. All right, so first of all, sorry, I lost my pen here. So when you've got a right triangle, remember you have to have a 90-degree angle on one side. All right, the side that does not touch the right angle is always called the hypotenuse. All right, and then the other two sides are called the legs. All right, so in this example here, side Z is the hypotenuse and X and Y are the legs. Because it is a right triangle, that allows us use of the Pythagorean theorem, which says a squared plus b squared is c squared, or for us, leg 1 squared plus leg 2 squared is hypotenuse squared. Hopefully you know that. All right, let's see, next. It also buys us three trig functions, three trig functions, sine, cosine, and tangent. Please remember, sine, cosine, and tangent are trig functions for which the input is an angle, so you can take the sine of 40 degrees or the cosine of 80 degrees or whatever. It does not make sense to find the sine of $5, okay? Your input has to be an angle, and then your output is a ratio. It's always going to be a ratio between the lengths of two sides of a triangle, okay? So in order to remember your three equations, we use this mnemonic device, SOHCAHTOA. So the SO part means that the sine of a given angle is equal to the length of the opposite side over the length of the hypotenuse. The CA part means that the cosine of the angle is equal to the length of the adjacent side divided by the length of the hypotenuse. And then the TOA part means that the tangent of the angle is equal to the length of the opposite side over the length of the adjacent side. So in order for this to make sense, you have to be able to label your three sides, opposite, adjacent, and hypotenuse. Well, the hypotenuse we already talked about. Your opposite and adjacent are dependent on the angle you pick. All right? In this class, our angle will pretty much always be the angle between the hypotenuse and the horizontal side of the triangle. All right? And the symbol that we're going to use for angle is the Greek letter theta. All right, it's basically a circle with a horizontal line through it that is the Greek letter theta, okay? Once you decide which angle you're looking at, and again in this class it'll always be between the hypotenuse and the horizontal side, that's going to determine your opposite and adjacent sides, all right? So the opposite side is the side that doesn't touch the angle. It's the side of the triangle that is on the opposite side of the triangle from the angle. So here I've got this yellow angle. The side that's opposite is the y side. So that's going to be my opposite side, which then means that my adjacent side is going to be x, because that is the side that touches the angle but is not the hypotenuse. Okay? And so for a given angle, for a given right triangle, the sine of this angle gives us the length of the opposite side over the length of the hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, okay? Sine, cosine, and tangent, because it gives you a ratio, there are no units on it, because it would be like foot per foot or meter per meter, and the units cancel out, so you just get this ratio, a decimal, okay? Cool. If you're looking at this right now and you're like, I have never learned that, or I learned that during a pandemic and I didn't actually learn it, then you need to find time to come in and talk to me, either before or after school, and I can show you how this works, okay? Because we are going to use these three equations again and again and again this year, okay? Oh, and this one, okay? So now you hopefully know that, and if not, please come talk to me. Really, you cannot do this class if you don't know this stuff, all right? So now, a couple quick definitions. Vector, scalar. So let's do scalar first. Let's talk about a scalar. A scalar is just a number where you count how much of a thing. How much pizza did you eat last night? 6 slices. Okay, that's a scalar. The number of slices of pizza you ate last night is a scalar. How much time did it take? 5 hours. Time is a scalar. How far did you drive? 30 miles. Distance is a scalar. How fast were you going? 10 miles per hour. Speed is a scalar. All right? Now, a vector is different from a scalar because it includes direction. All right? For example, remember we learned that the main difference between velocity and distance is that velocity includes direction. 60 miles per hour is a speed. 60 miles per hour west is a velocity. Okay? And that makes it a vector. And so we learned a little bit about sort of drawing those arrows to represent the vector. Okay? So position is a vector, right? You can be 2 miles to the left of the origin or 2 miles to the right of the origin. Okay? -2, +2. Displacement is a vector. You can go 2 miles west or 2 miles east. Velocity is a vector. You can go 40 miles an hour north or 40 miles an hour south. 40 miles an hour up, 40 miles an hour down. The direction matters. Similarly, acceleration of gravity is 9.8 meters per second squared down, which is why we always make it negative. And even force, which we haven't learned about yet, force is a vector. Force is how hard you push or pull a thing, okay? And so when you push or pull a thing, the direction that you push or pull it also matters, okay? Because there's a couple examples here, the units for force are what are called newtons. So you can exert a force of 5 newtons or 20 newtons in a given direction, okay? So if the direction is important, it is a vector. If it is not, it is a scalar. All right? So up until now, all of the vectors that we've done have been one-dimensional, right? When you throw a ball up into the air, oh, here we go. If you throw a ball up into the air, the starting velocity is 30 meters a second, and it's enough to just say positive 30 meters a second, because you know that positive 30 meters a second corresponds to it going up, right? And then later on, it's going to come down, and now the velocity is negative 30 meters a second. So when you're dealing with a one-dimensional vector, you can indicate the direction just by using a positive or a negative sign, okay? As long as you know the context, right? If the problem is about throwing a ball, then we know up is positive, down is negative, all right? If I tell you Esther walks 2 miles, saying -2 miles doesn't mean anything unless I tell you that she can either go east or west, okay? So the second example, Esther walks east 2 miles. So her displacement is positive 2 miles, and that works as long as I know that the only 2 options are east and west, okay? And then the displacement for Wally, so this is Esther, here's Wally. Wally's is going to be -2 miles, right? Because he's going in a negative direction, okay? So we've got a car driving forward. So here it looks like we're going to make forwards positive and backwards negative. So here we've got a car driving forwards and it's speeding up. So my acceleration is going to be positive 2.5 meters per second squared. Whereas my truck, even though it's driving forwards, it's slowing down. So now my acceleration is going to be negative 2.5 meters per second squared because this acceleration is working against my forwards velocity, right? Okay, so as long as all of your motion is linear, occurring in one dimension, positives and negatives indicate direction, all right? But the problem is in the real world, there are, more than just forward or backwards, right? We have sort of an infinite number of directions that we can travel, right? So in 2 dimensions, there's an infinite number of directions you can travel, right? So look. Oh, why did that not? No, it's not what I wanted to do. Hold on, let's try that again. Let's get ourselves an arrow. Here we go. Okay, so here's an arrow, right? So right now the arrow is pointing horizontally forward, right? So cool, right? But it could be vertical or anywhere in between, right? So there's sort of an infinite number of directions that this can go. So how do we distinguish between them? Okay, well, we could say it's going horizontally. We could say it's going down. We could say it's going up. But what if it's going at one of these weird angles, all right? So here's the deal. For the purposes of this class, there are basically 2 directions that are, well, if it's not horizontal or vertical, there are 2 categories of directions that it could go. So here's horizontal, right? If it's going like this, we're going to call that above the horizontal, whereas if it is going like this, then we are going to call that below the horizontal. All right? But we still need a little bit more detail, right? Because like when I do this, when I make this below the horizontal, I still need to decide, like there's an infinite number of below the horizontals, right? So which one of these do I want? And so to describe it, we need to measure an angle. And so the angle that you always measure is the angle between the vector and the horizontal line, okay? So for this above the horizontal vector, what you would do is you'd go, all right, well, this is horizontal, so this is the angle I would want. So if this is 30 degrees, for example, then that's 30 degrees above the horizontal. Okay, with this below the horizontal one, maybe this is 20 degrees. So now that's 20 degrees below the horizontal. All right, so you'll always be given the angle either above the horizontal or below the horizontal. All right, so for example, let's draw some of these. Oh, I gotta delete this guy and this guy. Out of my way, blue arrow. Okay, so here we go. So for this guy, a car drives 3 kilometers at 40 degrees below the horizontal. So below the horizontal means it's going forwards and down. Here's my horizontal, here's the 40 degrees, here's the 3 kilometers. So that's describing the displacement of the car. 3 kilometers, not horizontal, 40 degrees below the horizontal. Okay? Or maybe it's about Roy throwing a ball. But he's not throwing the ball straight up in the air, he's throwing it at an angle, 20 degrees above the horizontal. So here's above the horizontal, here's horizontal, this is the 20 degrees. So when he first throws it, the velocity is 32 meters a second this way, okay? All right, or maybe it's a force. Maybe Roy is pulling a rope with some amount of force. And in this one, it's 600 newtons at 50 degrees below the horizontal. So here's horizontal. 50 degrees is going to be pretty steep. Here's my 50 degrees. And then here's Roy's force of 600 newtons. Okay? So when you're talking about two-dimensional motion, a positive or a negative isn't enough. Okay? Because there's an infinite number of ways that you can be not horizontal, right? Okay? And so we need to give that angle to describe the exact direction. All right? Cool. So, unfortunately, we can't type these vectors into our calculator, right? You can't type 30 kilometers at 40 degrees below the horizontal into our calculator. So we need to figure out a way to do calculations using these vectors. And to do that, we consider what are called vector components, all right? And any given vector is going to have 2 components. There's a horizontal component and a vertical component, all right? And those components are a representation of the progress horizontally or the progress vertically, okay? So let's go back for a minute to this green example here. So our car is driving, maybe it's about a car driving down a mountain, right? And it goes, 3 kilometers down this mountain road. Well, as it does that, 2 things are going to happen. It's going to go forwards some distance, and it's going to go vertically down some distance, okay? So the length of this side is our horizontal component, and the length of this side is our vertical component, okay? So before I get too much further here, we should talk about sort of how you take a vector and make it into a triangle, okay? So there are basically 2 types of triangles you need to know, all right? Anytime your vector is above the horizontal means it's going to point this way. So let's call our vector v. I'm just going to use v for vector, whatever. Maybe it's a velocity vector, maybe it's acceleration, who cares, all right? So the idea is because my vector points forwards and up, there are 2 components. There's one component that points forwards. We call that the horizontal component. We're going to label it Vx. The x-axis runs horizontally, right? So we call this Vx to indicate that that's the horizontal component of v. All right? And then there's another component that points vertically. And we call that Vy. So to be clear, here's what the notation means. We've got some vector v, Vx is the horizontal component of that vector, and Vy is the vertical component of that vector. Here is the angle above the horizontal. Now, to be clear, couple things. One, the vector itself will always be the hypotenuse. The vector itself will always be the hypotenuse, okay? Which means that your right angle is always going to be between your x and your y components. And notice that your x and y components are always drawn so that the head of the x component touches the tail of the y component, okay? So any vector has two ends to it. There's the head and the tail, okay? When you draw your x and y components, when you draw your horizontal and vertical components, the head of the x component will always touch the tail of the y component, okay? And so notice in this problem, let me go back and redraw this, my original vector points forwards and up, right? Because it was above the horizontal. And as a result, it's forwards and up. So my horizontal component points forwards, and my vertical component points up. Modeling forwards and up, forwards and up, okay? Here's your right angle, here's your angle, all right? So this purple triangle that I just drew here is what will always happen if your object is going forwards and up, which we call above the horizontal, all right? If it's below the horizontal, you just take this and flip it over. Below the horizontal would be forwards and down. So here's my vector, and then the components need to be forwards and down. And notice once again, the head of my x component touches the tail of my y component. Okay? Once again, here's your angle, here's your right angle. Okay? Every single triangle you draw in this class for the next at least few sections is going to be one of these two. All right? The only exception, well, I'm getting ahead of myself. All right. So later on we'll learn about some exceptions, but for now, this is what you need to know. Please notice the vector is the hypotenuse. The components must be perpendicular. I can't stress that enough. I'm going to say it one more time. The vector is the hypotenuse. Pause and write that down. The components form the right angle. Okay? The x and y components form your right angle. Okay? Yeah, cool. All right. So that is how you draw the triangles. All right. So there are basically two types of problems you need to know how to do. Okay. The first type is a problem where I give you the vector and you have to find the components. All right. So in this one, it says a car rolls at 12 meters a second up a ramp inclined at 30 degrees above the horizontal. So you're given the vector. Let's see. The car is rolling at 12 meters a second at 30 degrees above the horizontal. So let's draw that. So here's my velocity vector for my car. 12 meters a second at 30 degrees above the horizontal. And now we got to find the horizontal and vertical velocities. So I'm going to draw in my components. Here's my horizontal velocity. That's the horizontal component of the vector. And here's the vertical component. Okay? So this represents how fast the car is moving forwards. This represents how fast the car is moving vertically. All right? So to solve this, we're just going to do SOHCAHTOA. We've got a triangle here, and we know one side and one angle. So let's go through and label our sides. So here's my right angle, which means this guy is my hypotenuse. Because this is theta, that means this guy is my opposite, and this guy is my adjacent. Okay? So, boop, boop, choo, choo. Whoop. Okay, so if I want to find the length of my opposite side, the only other side I know is my hypotenuse. So which trig function uses opposite and hypotenuse? Oh, that's so, right? So here we go. So the sine of theta is opposite over hypotenuse. So the sine of 30 degrees is opposite over hypotenuse. Okay. Oh, well now, so sine of 30 is just some number. So multiply both sides by 12. 12 times whatever the sine of 30 is equals Vy. Oh, punch that into your calculator. Make sure your calculator is in degrees. You get 6 meters a second is Vy. Notice the units on all three sides have to be the same. Okay, so over here, Vy, 6 meters per second, because our hypotenuse is also meters per second. Okay? All right, so that's my opposite side. Now we got to go over here and find our adjacent side. So let's do that. So now we got to find our adjacent side. Whoa, try that again. Let's find our adjacent side. So now I'm going to use the trig function that has adjacent and hypotenuse. Really, at this point, we know everything except the one side, so you could use tangent, cosine, or Pythagorean theorem. I almost always use sine to find the y component and cosine to find the x component. All right, so here we go. So cosine of theta is adjacent over hypotenuse. Cosine of 30 equals Vx over 12. Multiply both sides by 12. 12 times the cosine of whatever the cosine of 30 is Vx. And Vx turns out to be, if you punch this into your calculator, I figured it out yesterday and wasn't smart enough to write it down. Let me grab my calculator. On 12 cosine 30, 10.4 meters per second. Okay. Finally, check your signs. All right. In this class, pretty much your x component will always be forwards, so that'll be positive. Here, my y component points up, so that's also positive. Okay? It's okay, only your components can be positive and negative. Okay? The hypotenuse, you have to describe the angle. Your components, if I say Vy is positive, because it's a y component, it has to be up. Okay? And similarly, if the y component is negative, it's got to be down. And your x component in this class will pretty much always be positive. All right? So that's one of two types of problems you'll have to do, where you're given the vector and you have to find the components. Please notice my components are head to tail. Okay? And that indicates, that shows you the fact that because my x components are forwards and my y component is up, the overall vector is forwards and up. All right? So, last example. Sometimes you got to go backwards. So here we've got this a peregrine falcon that is diving, and you're given the horizontal and vertical components of the falcon. So notice the falcon has a horizontal component of its velocity of 30 miles an hour. It's positive, so it's going forwards and down. Oh, sorry. And down. All right? So my Vx is positive, my Vy is negative. So the falcon is going forwards and down. The falcon is going forwards and down. Okay? So now we can label stuff. Let's see, our Vx is 30 miles per hour. Our Vy is 40 miles per hour. We are trying to find V. Please remember, just finding the hypotenuse is not enough. You also have to find the angle. Okay? So, let's do that. So, first of all, Pythagorean theorem. Vx squared plus Vy squared is V squared, right? Because this is my hypotenuse. So 30 squared plus 40 squared is V squared. 2,500 equals V squared. 50 miles per hour is our velocity. Okay, but we also have to find the angle so that I can say how far below the horizontal it is. So what I want to do is choose a trig function that uses opposite and adjacent, since those are the numbers I was given. So, oh, that's tangent. The tangent of theta is opposite over adjacent. The tangent of theta is opposite over adjacent. Oh, I just realized I didn't do a thing. Technically, Vy here is negative, which is how I knew it was pointing down. When you use trig functions, don't worry about the negatives, okay? I'm going to take care of the negative in my answer when I say below the horizontal, okay? Please don't put negative numbers into your trig functions. All right, so this is the same as saying theta is the inverse tangent of 40 over 30. So here's where you use the shift button on your calculator, or the second button on your calculator. Let's see, on most of you guys have TIs, so it's going to be the second button. So you're going to hit second tan, and then in parentheses 40 over 30. All right, and the angle turns out to be about 53 degrees. So then my final answer is velocity is 50 miles per hour at 53 degrees below the horizontal. So there's your final answer. Please make sure you don't just give me the hypotenuse. You also need to give me the direction. Okay? That's it. It's just those two types of problems. Okay? We're going to add one other layer of difficulty to this a little bit later in the next chapter, but for now, that's all you need to know. All right? Cool.